Hello everyone, welcome to the course Semiconductor Devices and Circuits, which is being taught by Professor Sanjeev Sambandhan of IIC Bangalore. So this is a live problem solving session for this course. So this week we will be covering week one of this session of this course. So I am Mayank Goyal. I am a research scholar in the Department of Electrical Engineering, IIT Bombay. The course is being taught by Professor Sanjeev Sambandhan, who is a professor in the Department of Instrumentation and Applied Physics at IIC Bangalore. The course plan for this week is Exertion and Quantum Mechanics, where we are covering Schrodinger's equation, particle in a box, harmonic oscillator, etc. So this live session is happening every Sunday 6 p.m. to 8 p.m. at the Google Meet link, this one. So first we will do a recap of the lecture. So first we will do a recap of this lecture. This week's lectures. So this is a famous thought experiment by Feynman. So the experiment is that you have a marble gun which is throwing very small marbles at two slits side by side, and then there's a recording screen which is recording the uh, number of marbles hit at a particular position divided by total number of marbles fired, which is a probability. So first we close one slit and see how the marble distribution is, and we find and we see a curve like this, which is what you expect. Similarly, if you close the other slit and then you fire, you will get a curve like this, peaking at the center of the slit. So now if I open both slits, I would expect a curve like this, because the probabilities will add up, which is p1x plus p2x, and this will result in a curve like this, and maximum at the center, and then go, then slowly dying down. So this is the classical mechanical intuition that a marble can go through only one slit, one of the two slits. Now let's assume if instead of marbles we have a wave, and we do the same experiment and we record the intensity. Then if we close one slit, we will have an intensity like this, which is what is you get, which is what you get for waves. Similarly for this, but when you combine them, you don't get an intensity like this. Instead, you get these alternating bright and dark peaks. So because they, instead of just adding up, these both waves interfere using the formula I equals to I1 plus I2 plus 2 I1 I2 per half cos phi, which results in this type of behavior. And this is what we expect from waves, because wave fronts will go through both slits together, and then they will interfere. Now if we have electrons which are very small, and we see through both slits, then instead of getting a normal behavior which we saw earlier, we get a behavior similar to what we got for waves. How? Now we put a detector in front of the slits to see through which slit the electron is passing. And when we do that, we get this curve, which is what we expect from classical mechanics for electron for materials. So this results that electron is acting as both wave and particle. So we need both wave and particle like treatment to explain such experiments involving photons, electrons, etc., which behave as both particles and wave. So this duality is given using the de Broglie's equation, which tells that wavelength of the particle lambda is equal to h by p, where h is a Planck's constant and p is the momentum of the particle. So this is an example for electron, and this is an example for a tennis ball, which has a very high mass and very low velocity, whereas electrons have very high velocity. So there the wavelengths come out to be in nanometers, and here the wavelength come out to be 10 per minus 32, which is negligible. So we can assume zero wavelength. So we can say the tennis ball is not acting like a wave; it is acting like a particle only, a massive particle. So that is why we don't see wave particle duality in normal scenarios. We only see that when we have very small masses and very high velocities. So now few useful relations. K equals to wave vector equals to 2 pi by lambda. Note that K can also be used as Boltzmann coefficient, although generally we write KB for that. But you have to take that into context because it will be used in future. And then lambda equals to h by p, which we just read. So p will be equal to h by lambda, or we can also write it as h cross k, where h cross or h bar is the reduced Planck's constant, which is h by 2 pi, which is approximately 1.05 to 10 power minus 34 joule seconds. And from here we can then get the energy of the photon, which is h nu equals to hc by lambda, or it is also written as h cross omega, where omega is the angular velocity, which is equals to 2 pi v. Now Heisenberg's uncertainty principle, it states that you cannot measure position and momentum at the same time accurately. That is, there will always be an error in energy and error in time of measurement. So if delta x is the error in determining position and delta p is the error in determining momentum, then delta p delta into delta x will always be greater than h cross h bar by 2. So in general, a signal in time space versus frequency will always have this restriction. So if momentum is well defined, that is, we know the energy of the electron gun, then position will not be defined, and we will have to assume it as a beam, and we can't predict exact position of the electrons. And same for vice versa. So next we come to quantum mechanics. We start with the wave function, which is denoted as this symbol, which is called psi, psi, which contains information on all measurable parameters of a particle. So if we consider 1D, which is, let's say, x direction, the wave function is psi x comma t, and this is, then we say psi into psi star. So psi star is called conjugate. So psi can be an imaginary number also. So in maths, you would have studied conjugate of an imaginary number. That is what psi star denotes. So if you multiply psi into psi star, which is how you calculate the absolute value of an imaginary number. So that gives us the probability density of finding the particle between positions x and x plus dx. So if psi of x comma t is real, And then the probability of finding the particle between x and x plus dx becomes psi x comma t square dx. And the probability of finding the particle between x equals to a and x equals to b is square root of ab psi square dx. It's not square root, integral a to b psi square dx. So now we come to operators. So there are some measurable parameter. So some operators which are used to extract the parameters of a particle. First is a momentum operator, which is P of x equals to h cross by iota dou by dou x. So dou is your partial differential, which will give so thus h cross by I dou psi by dou x will give you P of x into psi. Only energy operator E equals is will be E will be minus h cross by iota dou by dou t, which will give us minus h cross by iota dou psi by dou t equals to E psi. So be careful here. You see this symbol over px and e. So this is called hat operator, and this denotes that this is a quantum operator and not a number. So then the kinetic energy is given as p square by 2m, which is 1 by 2m h cross by iota dou by dou x, and then same thing inside h cross by iota dou psi by dou x. So you multiply this, you get minus h cross by 2m dou square psi by dou x square. So now properties of the wave function. So psi must be a solution of the Schrodinger's equation. We'll come to that. Psi must be continuous. D psi by dx must be continuous. So psi should be continuous, and its derivative should also be continuous. And psi must be normalized. That is, it cannot blow up. So that is psi square dx from minus infinity to it must be equal to 1, because as we learned earlier, this is a probability. This is probability of finding the particle. So the probability of finding the particle from minus infinity to plus infinity has to be equal to 1, because the particle should exist. Now the Schrodinger's equation. So we know that total energy of a particle is given as kinetic energy plus potential energy. So the potential energy will depend on the potential terrain the particle is placed in, which is and it is given as V psi. And kinetic energy, we know, we just learned kinetic energy is given as minus h square by 2m dou square psi by dou x square. Potential energy we just learned plus V psi. And energy term we had learned that it is minus h cross by iota dou psi by dou t. Now this equation incorporates what x and t. Now if a particle is in time equilibrium, that is, it is not changing with time, its state is not changing with time, then we change it to a time independent Schrodinger equation, which is given as minus h bar square by 2m dou square psi by dou x square plus v psi equals to e psi. So now we will use this Schrodinger's equation. So first we consider a case which is called particle in a 1D box with within infinite potential barrier. So we draw this, which is distance versus potential, and so between 0 and L the potential is 0. So this is 0 potential, but before 0 the potential is infinite, and after L the potential is infinite. So that means in an infinite potential there cannot be any particle. Particle has to be between 0 and L. So we use this equation, minus h square by 2m dou square psi by dou x square plus b psi equals to e psi. So we know that v is equals to infinity outside the outside 0 and L, and v equals to 0 inside 0 and L. So inside the box we write this, we write v equals to 0, so we get this. And if we solve this, we will get psi equals to a sin kx plus b cos kx. So so we have assumed psi as a sin kx plus b cos kx. Now we know that psi must be continuous. So for that we have to remove cos kx, because this term cannot, because because at x equals to 0, we know that psi is 0 because particle cannot exist in the infinite barrier. So psi is 0 at x equals to 0. So now if we put x equals to 0 here, cos 0 will be 1. So we cannot have psi equals to 1, because psi has to be 0 at x equals to 0. So then we'll have to put b equals to 0. So then it only a sin kx term will remain. And if we put if we put differential also, then and we equate it for x equals to L, we will put x equals to L equals to psi of x equals to L equals to 0, we will get this equation, psi equals to a sin n pi by L 1. And now we know that since the particle is restricted within 0 to L, so we can just ignore the minus infinity to 0 and L to infinity terms. We know that between 0 to L the probability is 1. So we put that and we can then calculate the energy equals to En equals to n square pi square h bar square by 2m L square. So for n equals to 1, this will be the state. For n equals to 2, it will be like this. For n equals to 3, it will be like this. The wave function of the particle. Now, now we can also have instead of 1D box, we can have a 2D box with infinite potential barrier. So there, instead of, we'll have both x and y terms independently. So now you can just, it's similar to 1D, it will be 2D, and you just get two terms for energy, one for x term and one for y term. Now we have now we have finite potential barrier. So now since this is finite, so we cannot ignore these regions. Here also we will have the Schrodinger's equation with plus v naught psi. In the middle, it's the psi v is 0. So here the potential term is 0. So now now we have three equations. So we'll have three different psi functions for each region, and we know that the energy has to be less than v naught, because if energy is greater than v naught, then the wave part will be here and it won't be bound by this box. It will be a free particle then. So this equations won't satisfy. So energy has to be less than v naught. So we can convert this term. You can bring this term here and this term here. So that will make us this. So we can then write this term as alpha square, because we know v naught minus e is has to be greater than 0. So this term has to be positive. So we can write it as alpha square. Same for psi 3 also. And for psi 2, we can write it as, we can bring this here and we can get this term. Now 2me by h bar square has to be positive because energy has to be positive. So we can write this as k square term. And now we can, by quit, now we can assume from, now we can solve these three equations, and we get, by solving these equations we get these generalized formulas, where psi1 is a1 e power alpha x plus b1 e power minus alpha x. Similarly, psi3 will be a3 b3, and psi2 will be e power iota kx and e power minus iota kx. So now we will put the equation. Now we will put the restrictions we have. So we know that if as x is approaching minus infinity, the the second term will approach infinity, and that will blow our equation, and we cannot then normalize it to psi squared dx equals to 1, which means v1 has to be 0. So psi1 has to be a1 e power alpha x. Similarly, for psi 3, x as x approaches infinity, this will approach this term will approach infinity. So psi 3 will then be just b3 e power minus alpha x. Now, now within the box, we know that the wave function has to be symmetric around x equals to 0, because the our this structure is symmetric. So the structure is symmetric around this x this point. So our wave function has to be symmetric around this point. So that will give us psi 2 equals to k2 sin kx, or psi 2 equals to k2 cos kx. So it can be odd symmetry or even symmetry, depending on it can be sine or cos. Now we use now let's assume this. So now we can just now we put the continuity equations here. So then psi 2 x L by 2 should be psi 3 x L by 2, and so that will give us the relationship between psi and k and alpha, which will come out to be tan k L by 2 equals to alpha by k. And if we assume sin k, then we get cot k L by 2 equals to minus alpha by k. So now you see, now the particle is not restricted to within the box also. It is particle is also coming out of the box, which should not be possible since the energy is less than the potential. So the particle should not be existing outside the box, but it is existing outside the box. So that is one special thing about quantum mechanics, that that you can have particles existing within potentials, high potential regions also. And this is phenomena is called tunneling, and this is a very useful phenomenon. Next we come to harmonic oscillator. So a harmonic oscillator is a oscillator which oscillates within a parabolic potential. So the potential here is given as v equals to f x square by 2, and here you can get omega equals to f by square root of f by m, which gives us v equals to m omega square x square by 2. So then we put that here, and we take a psi is e power minus alpha x square by 2. If we put that inside this, we get this equation. So this gives us alpha equals to m omega by h bar and E equals to h cross omega by 2. So this is the ground state energy. Similarly, we can calculate for higher states also. So it should be just n h cross omega by 2. So now some practice questions. So according to Heisenberg's uncertainty principle, del P del X is greater than equal to h cross by 2. If a hypothetical measurement determines the exact spatial position of an electron with infinite accuracy, that is delta x equal to 0, what is the mathematical consequence for the particle's momentum? The momentum is also determined with zero error, establishing a stationary quantum state. The momentum becomes entirely zero, halting the particle's motion. The error in the momentum measurement becomes exactly h cross by 2. The error in the momentum measurement becomes infinite large, meaning the momentum is entirely undefined. You can speak or write your answers in the chat. Anyone with the answer? So that is correct. The answer would be D. So the Heisenberg uncertainty principle dictates that a position is known perfectly. Then the uncertainty in momentum must approach infinity to satisfy the inequality, which means momentum is completely undefined and you cannot measure the velocity of the particle, which means you cannot calculate the energy of the electron if you have the position with infinite accuracy. When analyzing the wave function psi x comma t to extract physical observables, operators are utilized. What is the precise mathematical operator for the kinetic energy of a wave particle in one dimension? H bar by iota dou by dou x minus h bar square by 2m dou square by dou x square minus h bar by iota dou by dou t half m omega square x square. Anyone with the answer? So the answer would be B minus h bar square by 2m dou square by dou x square So we know the momentum operator Px hat is given as h bar by iota dou by dou x, and we know that kinetic energy is p square by 2m. So we apply px by into px divided by 2m, and that will give us minus h bar square by 2m dou square by dou x square. According to the physical constraints imposed on a quantum mechanical wave function psi x comma t, which of the following scenarios would render a proposed wave function mathematically invalid for representing a particle in space? Psi of x takes on a complex numerical value rather than a strictly real value. The first derivative of the wave function d psi by dx is continuous across a boundary. The amplitude of uh, psi of x scales at e power alpha x, where alpha greater than 0, x approaches infinity. The integral of psi x mod square dx evaluates from minus infinity to infinity equals exactly 1. So the correct answer to this would be C. So a physically acceptable wave function may be complex valued. So A is not an invalid argument. Uh, and for finite potentials, both the wave function and its first derivative are generally continuous. So B is also valid. And a normalized wave function has to satisfy integral minus infinity to infinity psi x square dx equals to 1, which makes D is valid. But if psi of x is proportional to e power alpha x, when alpha is greater than 0 and x is approaching infinity, then psi x square is proportional to e power 2 alpha x, and x is approaching to infinity, e power 2 alpha x will also approach to infinity, which means psi x square will also approach to infinity, which means the integral will will not be equal to 1, and the, as such wave function cannot be normalized. It is mathematically invalid to represent a particle in space. An electron mass m equals to 9.1 into 10 power minus 31 kg, q equals to 1 minus 1.6 into 10 power minus 19 coulomb, is fired from an electron gun with a velocity of 1 into 10 power 5 meter per second. What is the approximate calculated kinetic energy of this electron in milli electron volts? 14.2 MeV, 28.4 MeV, 7.55 MeV, 72.5 MeV. Anyone trying to solve this equation? Solve this question? Please write answers in chat. you have answers, you can either speak it or write in the chat. Or if you have any doubts, you can also then also you can speak or write in chat. That is correct. The answer will be 28.4 MeV. So the kinetic energy is, we write it as half mv square. So mass we know is 9.1 into 10 per minus 31, and velocity we know as 0.10 per 5 milliseconds. So we multiply that, we get 4.55 into 10 per minus 21 joules. Now to convert this to electron volts, we divide it by the charge of the electron. So we divide it with, we get 28.4 into minus 3 electron volts, which gives 28.4 milli electron volts. Using Planck's constant h equals to 6.6 into 10 power minus 34 joule seconds, what is the exact de Broglie wavelength of the electron described in the previous question? That is, velocity equals to 1 into 10 power 5 meter per second and mass is 9.1 into minus 31 kg. A 7.2 nanometers, B 9.1 nanometers, C 7.1 micrometer, D 9.1 in 10 power minus 32 meter. That is correct. The answer will be A, 7.2 nanometers. So first we calculate the momentum using as P equals to mv, which comes out to be 9.1 into 10 power minus 26 kg per meter second. And then we calculate lambda equals to h by p, which is 6.6 into 10 power minus 34 divided by 9.1 into 10 power minus 26, which comes out to 7.2 into 10 power minus 9 meters, that is 7.2 nanometers. When deriving the allowed wave function for a particle in a 1D infinite potential well from x equals to 0 to x equals to L, the general solution is initially written as psi of x equals to a sin kx plus b cos kx. Why does the coefficient b mathematically evaluate to exactly 0? A. The cosine function is mathematically incapable of being normalized over a finite region. B. The wave function must be continuous, and since the potential is infinite outside the box, psi of 0 must equal 0. Setting x equals to 0 forces b equals to 0. C. Cosine functions represent imaginary energy states which are physically forbidden inside a potential box. D. The cosine function violates the Heisenberg uncertainty principle for a confined particle. So that is correct. The answer will be B. So a fundamental property of the wave function is continuity. So outside the infinite well, the wave function is absolutely 0. So therefore, exactly at the boundary x equal to 0, psi must equal 0. And since sine of 0 is equal to 0, but cos of 0 equals to 1, the equation forces the constant b to be 0. So only the sine term will remain. In the quantum mechanical model of a particle interacting with a finite potential barrier of height V0, what is the physical meaning of total energy E being less than V0? That is E less than V0. The particle possesses negative kinetic energy in classical terms, yet quantum mechanics predicts a non-zero probability of finding the particle inside the barrier. The particle is completely repelled and perfectly reflects off the barrier as a continuous wave. The potential barrier becomes infinitely high, permanently trapping the particle in region 2. The particle accelerates and gains a wave vector of infinity upon hitting the barrier. So the correct answer would be A. So if A is less than V naught, classical physics states that the particle cannot exist in the barrier region because it implies negative kinetic energy. Because kinetic energy plus potential energy equals to total energy, and if total energy is less than potential energy, that is only possible if you have negative kinetic energy. However, on solving the Schrodinger's equation, we get an exponentially decaying wave function inside the barrier, which proves that there's a non-zero probability of the particle existing in this classically forbidden region. So classically it's forbidden, but quantum mechanically there's a non-zero probability that there will be a particle here, and it will be exponentially decaying as it goes further inside the barrier. The phenomenon where a wave function exhibits a non-zero exponentially decaying profile within a classically forbidden finite potential barrier, that is E is less than V naught, is practically utilized to facilitate operation in which of the following devices: the focusing lens of an electron microscope, the wave generator in a macroscopic ripple tank, the carrier injection across source drain regions in a MOSFET, and the surface probing mechanism of a scanning tunneling microscope, that is STM, the acceleration chamber of a linear particle collider. So the correct answer is C. The exponentially decaying wave function outside the classically allowed region is represents quantum tunneling, and so engineers rely on this mechanism for electron injection of MOSFETs, which you will study later in this course. And it is also a direct it is the direct operating principle of the scanning tunneling microscope. So in scanning tunneling microscope, a very fine metallic tip is kept just above very at a very small distance above your sample, and then electrons tunnel through the air from the tip to the sample, and that is how scanning tunneling microscope works. And in MOSFETs, there is a very thin uh, insulating layer your uh, between your contact region and your ma- device, and the electrons tunnel through that insulating region. So that is how tunneling is utilized in MOSFETs. When writing the Schrodinger equation for a quantum harmonic oscillator, the classical restoring force of a spring is modeled. In terms of mass v, m, and angular frequency omega, what is the exact expression for the potential energy B inserted into the Hamiltonian? V equals to m omega x, V equals to half m omega square x square, V equals to half m square omega x square, V equals to h bar omega x square by 2. So answer to this would be B. V equals to half m omega square x square. So we have the nat natural oscillation frequency relation omega equals to square root f by m. So which where f is the spring constant. So now rearranging it, we get f is m omega square, and the potential energy for a spring is given as half f x square. And if we instead of f write m omega square, we will get v equals to half m omega square x square, which we can then plug into the Schrodinger equation. So you can see here that this is a parabolic. This is parabolic potential that is like this. and the particles are within the restricted within this potential. If an electron's wave function is modeled as a simple plane wave, psi x comma t equals to e per iota kx minus omega t, and then applying the generalized momentum operator extracts the momentum parameter. What exact physical quantity is extracted if you apply the energy operator E hat equals to minus h cross by iota dou by dou t to the same plane wave? A. H bar k representing spatial momentum. B. H bar omega representing the total energy of the wave particle. C. Minus H bar k representing reverse momentum. D. 0, since a plane wave cannot possess total energy. So the answer to this is B. So applying the energy operator minus h cross by iota dou by dou t involves taking the time derivative of the wave function, which pulls down a factor of minus iota omega, and you multiply it with minus h cross by iota yields h bar omega. And because h bar omega is equal to h nu, this correctly responds to the total energy. So that is why this minus h bar iota by iota dou by dou t is used to represent the energy operator to give total energy of the wave particle. So now some bit complicated questions. An electron is confined in an asymmetrical 2D rectangular box with strictly defined orthogonal dimensions Lx equals to L and Ly equals to 2L. The total sum is the sum of independent special components, that is E equals to Ex plus Ey. Which of the following quantum state pairs Nx, Ny yields the exact same total allowed energy, thereby exhibiting the quantum mechanical phenomenon of energy degeneracy? A. The states Nx equals to 1, Ny equals to 4, and Nx equals to 2, Ny equals to 2. B. The states Nx equals to 2, Ny equals to 1, and Nx equals to 1, Ny equals to 2. C. The states Nx equals to 1, Ny equals to 2, and Nx equals to 2, Ny equals to 4. D. The states Nx equals to 3, Ny equals to 1, and Nx equals to 1, Ny equals to 3. Anyone trying to solve this answer? So the answer to this would be A. So the total energy in a 2D box is given as equals to pi square h bar square by 2m nx square by lx square plus ny square by ly square. Now Lx is L and Ly is 12. So you put that here, it becomes Lx square plus Ly ny square by 4, which can be multiplied by 4 and write it as 4nx square plus ny square. And that 4 then we can take it outside and make it to 8m. It won't matter since we are talking proportions. Now if we put 1 comma 4, then this nx equals to 1 and ny equals to 4, we get 4 plus 4 square, that is 20. And if we put nx equals to 2, ny equals to 2, we get 4 into 4 plus 2 square, that is 4, that is also again 20. So we see that for A, both the terms are equal to 20. So since the nx and y are different, both are distinct spatial states. There is no relation between them. They are distinct, yet they have the same total energy. And this is known as energy degeneracy, where two different states belong to the same energy level. So that is, we can say that one energy level can have multiple quantum states. This, this is known as energy degeneracy. And this is also a very important phenomenon in quantum mechanics. A quantum harmonic oscillator acts as a fundamental theoretical model for atomic vibrations. Given the effective mass m and a classical spring constant F, the natural angular frequency is omega equals to square root F by m. If a physical modification mathematically stiffens a molecular bond, increasing the spring constant F exactly by a factor of 9, while keeping the effective mass identical, how does the absolute lowest possible energy state, which is also called 0 point energy or ground state energy, of the oscillator mathematically change? It increases by a factor of 9, it increases by a factor of 3, it decreases by a factor of 3, it remains fundamentally unaffected because ground state energy is classically always exactly 0. So that is the correct answer. The answer will be B. So the 0 point energy or the ground state energy for a quantum harmonic oscillator is mathematically derived as E equals to h bar omega by 2. And because the angular frequency f is proportional to the square root of the spring constant, that is omega to square root f by m. If we multiply f by 9, then omega will be multiplied by square root 9, that is 3. And that when we put into energy, the energy total ground state energy scales proportionally and increases by a factor of 3. So the correct answer would be it increases by a factor of 3. For an electron trapped in a 1D infinite potential box, the energy states are given by En equals to n square pi square h bar square by 2m L square. If the ground state energy n equals to 1 for a specific box is mathematically defined as E1, which is what is the exact calculated numerical ratio of the energy gap between the fourth and third energy states delta E43 compared to the ground state energy E1. A1, B3, C7, D16. So C is the correct answer, 7. So when we put n equals to 1, we get E E1 equals to pi square h bar square by 2m L square. So we can write En as n square E1, and the gap between the fourth and third states, that is delta E43, is equal to E4 minus E3. That is 4 square minus 3 square into E1. That is 16 minus 9 E1. That is equal to 7 E1. So the ratio of this energy gap to the ground state energy is exactly 7. For an electron enclosed in a 1D infinite potential well, perfectly spanning from x equals to 0 to x equals to 12 nanometers, the particle is excited from the ground state up to the n equals to 3 state, disregarding the physical boundaries of the box, that is, not considering x equals to 0 and x equals to 12. What at what exact internal spatial coordinates x is the calculated probability of locating the electron exactly 0? A 4 nanometer and 8 nanometer, B 3 nanometer, 6 nanometer and 9 nanometers, C 6 nanometers only, D 2 nanometer, 6 nanometer and 10 nanometers. That is correct. The answer will be A 4 nanometer, 8 nanometer. Uh, So if we solve, so the general wave function for an infinite 1D infinite potential well is given as psi of x equals to square root 2 by L sine n pi x by L. Now we have n equals to 3 and L equals to 12. This will become sine 3 pi x by 12, that is sine pi x by 4. And the probability density will be 0 wherever the wave function itself crosses 0. And these points are called nodes. So nodes are the points where the wave function is crossing 0. So now we have sine pi x by 4 So now we want to make it 0. But so this will become 0 when pi x by 4 is a multiple of pi. So that will happen that will be 0, pi, 2 pi, 3 pi, etc. So if we put pi x by 4 equals to 0, we will get x equals to 0. If we get pi x by 4 equals to pi, we will get x equals to 4. If we get pi x by 4 equals to 2 pi, we will get x equals to 8. If we get pi x by 4 equals to 3 pi, we will get x equals to 12. So now we are not considering x equals to 0 and x equals to 12. So the only points remaining are x equals to 4 nanometer and x equals to 8 nanometers. So these 2 points are nodes in this wave function. So if I am drawing this wave function, this is 0 and this is just 12, then my wave function will go something like this, where this point will be 4 and this point will be 8. And you can also see the relation for a 1D infinite potential well. The number of nodes will be 1 less than the state. So for n equals to 1, there will be 0 nodes. So the wave function will go just like this. For n equals to 2, there will be 1 node. The wave function will go like this. For n equals to 3, there are 2 nodes as we saw just now. Similarly, you go higher, the node number of nodes will be 1 less than n. So that is all I had for today. Thank you for joining. If you have any doubts, you can ask in the chat or by speaking, or you can also leave the chat. You can also leave the meeting if you are okay.